Example number 2, I'll do 3 and then I'll set you to work. Let's try, if you would try this one at your table, at your desk, in your comp book. N goes from 1 to infinity of,
John, the last problem converged at 1.
there.
He saw it.
All right,
In case you didn't see.
Can you do that one?
Just one.
Just one. So what's that series look like? It doesn't have an n to put the 1 in, or a 2, or a 3,
Is
or
it
a
just
4.
1, 1, 1 plus 1 plus 1
It
plus 1
is,
plus 1?
very good. So when n is 1, we get a 1. And we get our plus sign. When n is 2, we get a 1, because there's no n in the term. When n is 3, etc. So we're going to go on forever like that. What's the generator there?
1.
1.
Wait,
Or
what do you-
N.
What do you mean by
Very
when you
good.
say generator?
I need an expression that I can always put in 1, then 2, then 3, and generate this.
Oh.
All right, so not yet. We don't need that just yet.
Is it
Let's
n
go
sub
ahead
0?
then and do the partial sums. Partial sums.
Or just N.
All right.
It's just N.
It can't be just n. If you put a 3 in, just n.
You just put in ones.
You
Brendan,
can't
you're
though.
putting
It's
in
1,
1, 2,
2, 3.
We'll see. It'll become clear. We were kind of ahead of ourselves.
We were
All right.
ahead.
So the partial
To the zero.
sums. What's
We're
the
ahead of
first
ourselves.
sum? What's the first partial sum according to how we get partial
1.
sums? All right. So the first partial
2.
sum is 1. Then the second one is 2,
You're right.
3,
I was thinking of the first part.
5. All right. So now,
You're right,
Brendan,
Brendan.
what's the generator for that?
N.
Okay. Does that make sense now?
That was a good try.
I was
Because-
thinking of the
Aaron,
first
yours
one.
made a lot of sense though.
So
I
when
give you
n,
props.
no, when he increments, when n is 1, you get 1. When n is 2, you get 2. So it does generate this list of partial sums, which is now a sequence. So is that converge or diverge?
Diverge.
What do you think?
It goes to infinity.
It goes to infinity. So it
True
is
chain.
divergent. So the limit of n as n goes to infinity is just infinity. There's no algebraic trick we can pull out for n. Divergent. Okay. All right, the last example will be a little more interesting than that one. You need more time with it?
He can pause it probably.
How about you?
Oh, no.
You don't have a pause button. Anyone else?
Nope.
Okay. Third and last example, so make sure you're getting what's going on and ask if you're not. Let us look
Sorry,
at
John.
a situation like this. N equals 1 to infinity of 1 over n minus 1 over n plus 1. So first of all, generate the series, not the sequence related to the partial sums, but just the series itself. So you're going to put in a 1. And would you keep it in parentheses? I know, like the first one, you could say, what's that, 1 over 1 minus 1 over 2, right? You could change that to 1/2, but you'll be able to see the pattern better if you leave it like that. So then you'll have your plus sign, and then you'll fill in when n equals 2, and n equals 3, and so on. All right, what kind of numbers are showing up in these brackets? What's the next one, Gianni, after this? When n equals 2,
It's 1/2 minus 1/3.
and then,
1/3 minus 1/4.
and then,
1/4 minus 1/5.
okay, and so on. Oops,
Oops, did this wrong.
1/5. All right, were you seeing where he got those numbers? By just putting in first the 1, 2, and so forth. Now, make sure you have your plus signs. Does this converge? Well, the way we tell is we change it to a sequence of partial sums. So the partial sums is first the first one, and then 1 plus 2, and then 1 plus 2 plus 3, and then 1 plus 2 plus 3 plus 4. We're going to march down the row like that. Do we really have to write this one out? Do you see a pattern that's going to happen no matter what with this one? What's happening with the partial sums here? Well, let's go ahead and write it out. So, Aaron, you give us the first one. We will. Let's go ahead and reduce this now.
1/2.
All right, Brendan, to you. We're gonna. What's this one become?
Oh. What? Yeah, 1/6.
1/6. So 1/6 plus 1/2 will give us this
4,
value,
6.
right? Which is 2/3.
2/3.
Okay. All right, Morgan, you're up at the
Okay.
fraction back. All right, so we already got to here is 2/3. So you have to add 2/3 plus whatever this is. You might need
It's 1/12, so it's
2/3 plus 1/12.
it's 9/12.
3/4.
9/12, which is 3/4. Good. All right, Gianni. We are going to add 3/4 to this. What's 1/3 minus 1/4?
Did we just do
Oh,
that?
1/3. Yeah, we're over here. 1/4 minus 1/5.
That would be 1/20th.
All right, and 1/20th plus 3/4.
4/5.
All right, I think you saw the pattern here. Okay, so that's cool. When we do that, then this one
I need
is.
one more hours.
All right. This one we can find the general term better. So Aaron, what is the general term that will generate this sequence with ends? So if I put a 1 in, it'll give me 1/2. If I put a 2 in, it'll give me that.
And
N over n plus 1.
Right, yay, okay. All right, so does this converge? We have to take that general term and take the limit of it and find out. So does that converge or diverge? N over n plus 1. So looks like our friend L'Hopital.
What am I doing?
So Brendan, L'Hopital this for me,
infinity over infinity.
and then
So you get 1,
over
and then over 1.
1 over 1, right?
So then it goes to infinity, so diverges.
No, because what's the limit? As
I'm
n of-
stupid. Never
what's
mind.
the what's the limit as n approaches infinity of 1? It is 1. So
Did you say it was
therefore
infinity?
converges.
Yeah,
Like it's
that's-
infinity, so it diverges.
All right,
I put the infinity in for 1.
all right. I need to make a
How do you
point
do that?
about this
Aaron.
one. The reason I kind of left it up like this, do you notice something about this? Let me get a different, this particular kind of problem. Look at this. And then,
The same.
so notice the negative 1/2 is going to cancel out the positive 1/2, and the 1/3 negative and 1/3 are going to cancel, and so on down the line. So this, when that happens, we are. So do you see how the 1 remained? And there it
Ooh.
appeared right there. So this is a special
Snazzy.
sequence. So I can teach it in theory, but I thought I'd teach it by example. And we did it without the method that I'm going to give you now. But this has a special name. It's called telescoping.
Ooh. Is it because when you look in one side of the telescope, you can wait?
Now,
my
have you ever
doesn't
seen
make
those
sense.
ones that those old time telescopes? Or I guess they weren't real, like the ship's captain would have. It looks like this. And you can
Oh yeah.
And you
they
can
have them at
smush
kids'
it up.
playgrounds.
squish it up like that. So that's the telescoping.
Like the
So-
ends are the same, and when
Yeah,
you push them together,
right,
you
right. So that's where the name telescoping comes from. How we doing for time now?
We are 9:30.
Okay. This telescoping type of problem, well, now I can give you the theory and show you some of these aren't as easy to come up with like that. So when that happens, you can skip all this and just do these kind a different way. So that's what I'm gonna present, it'll be the last thing. So why don't you start a new thing, let me get some board space.